Today we will discuss about a special category of homogeneous catalysis, that is acid-base catalysis. The mechanism of acid catalyzed reaction involves an equilibrium in which there occurs a transfer of proton from an acid to a substrate represented as S. Here S is the substrate, HA is a particular acid. The rate of the forward reaction is K1 and the rate of the reverse reaction is K-1, and the product is of this particular reaction is SH plus and A minus. Now this SH plus reacts with water and produces the product and H3O plus, and the rate of this reaction is K2. Now look at this overall reaction. Here the first step is an equilibrium or a reversible process, and the next one is an irreversible process. Now the rate of appearance of the product with respect to time can be written as the rate of appearance of product. This can be written as K2 to SH plus. Right? This is equation number 1. Now here the concentration of water is not included in this expression. The concentration of water is not included in this expression because its concentration does not change appreciably during the course of the reaction. Since the concentration of water is very high compared to the other species, therefore its concentration almost unaltered during the course of the reaction. Since it is almost constant, therefore its concentration is not included in this expression. Since now we are going to apply the steady state approximation to SH plus. Since SH plus is an intermediate, Now what is steady state approximation? SH plus is an intermediate. In this step, SH plus is produced in the reverse reaction. It is decomposed, and in the next step also it has been decomposing. So if we apply steady state approximation, then now at a certain time there will be a situation when the rate of formation of SH plus will be equal to the rate of disappearance of SH plus, and at that particular moment the concentration of SH plus is going to be fixed, and if we differentiate it with respect to time, then the value of the differentiation should be equal to 0. That is steady state approximation. So this is equal to 0 obviously at steady state, and is equal to, since in this step this intermediate is produced, in the next step in the reverse step, this intermediate is decomposed, therefore this negative sign, and in the next step also this particular intermediate is decomposed, therefore also a negative sign. Here also the concentration of H2O has been ignored, since its concentration remain almost constant during the course of the reaction. From this reaction we further obtain the concentration of SH plus is equal to and let it be equation number 3. Now substituting the value of equation number 3 into equation number 1. So the rate of the reaction is going to be finally we can write this is equation number 4. Now there are two specific cases. One is case 1. When K2 is very greater than K minus 1 into concentration of A. In that particular situation, this equation number 4 will be transformed like this. Since K2 is very greater than K minus 1 into concentration of A, therefore we can ignore this particular quantity. And the equation becomes like this. Suppose this is equation number 5. Now look at here. Here the rate of the reaction is first order with respect to the substrate, as well as it is first order with respect to the acid molecule. First order with respect to substrate and first order with respect to the acid molecule. This type of reaction is known as general acid catalyzed reaction, and this condition is known as general acid catalysis. General acid catalysis. Now let us move to case 2. When K2 is very less than K minus 1 into concentration of A minus 1. So in equation number 4 we will neglect K2, and the equation number 4 will become like this. We can represent it also like this. Now let us consider our dissociation reaction like this. The equilibrium constant of this reaction can be represented as this one, and if we rearrange a little bit, then we can write okay. Now substituting this value into this equation, suppose this is equation number 6. So substituting these values into equation number 6, we are going to obtain equation number 7. Here the reaction rate depends on the hydrogen ion concentration, although the proton is initially transferred from HA, and in this situation the reaction is said to be subject to specific hydrogen ion catalysis. Specific hydrogen ion